So I'd like to solve this problem that was on the quiz from the other day, and we have a 50 volt supply and we have a dependent voltage source. The dependent voltage source has an output voltage of 2Ix, where Ix is measured in this direction at the terminals A and B. So the question is, how do we solve this circuit? And the answer is we solve it the same way we solve every other circuit that we've ever looked at. We need to determine, if we want to know the Thevenin and Norton circuits, we need to determine the open circuit voltage, we need to determine the short circuit current, and we need to determine the Thevenin resistance, which is the same as the Norton resistance. The open circuit is the easiest of them all. When the terminals A and B are open circuited, Ix is equal to 0. It can't be anything else because the terminals are open circuited. Therefore, the output of this voltage source is 0. And if there's 0 volts dropped across that dependent source, then the open circuit voltage is 50 volts. So V open circuit is equal to 50 volts. Alright, there's one of the three things that we need to know. Now, looking at I short circuit. If we take terminal A and B and we short circuit them together, and we are looking for the short circuit current down through that shorting wire. We're left with a circuit that has two elements in it, both of them being voltage sources, and we say, how do we solve that circuit? Well, superposition is not going to work so well for us. In fact, nodal analysis isn't going to work very well because there are no essential elements, no essential nodes in this circuit, and in fact it's all one big supernode, so it's a little difficult to see how nodal analysis will help, and we're left with mesh analysis. So we'll write the KVL expression around this loop, and we say that 50 volts plus 2Ix is equal to 0. Solving for Ix gives us minus 25 amps, but we recognize that Ix is the opposite direction to I short circuit. Therefore, I short circuit is equal to 25 amps. Well, we've got V open circuit, we've got I short circuit. We can say that R Thevenin is equal to V open circuit divided by I short circuit, which is equal to 50 volts divided by 25 amps, which is 2 ohms. So our Thevenin equivalent has a 50 volt source in series with a 2 ohm resistor, and our Norton equivalent has a 25 amp source in parallel with a 2 ohm resistor, or that could be a 1/2 mho conductance. Right, so those are our Thevenin and Norton equivalents. I want to show you that there's still, we could have found our Thevenin directly, but it requires a little bit of work. If we wanted to know what our Thevenin directly is, we would remove the effect of all independent sources. So I'm going to replace this 50 volt source with a short circuit, and that leaves me with a circuit that looks like this. So I have a dependent source. The independent source has been shorted out, and we're interested in finding the equivalent resistance looking in terminals A and B. There are no resistors there. So many of you made the assumption that the resistance was equal to 0, but that's not true. When you have dependent sources, you have to give them a source of power. And so we were going to have to put on some sort of source and that source is going to energize the circuit. And when we determine the ratio of the current to the voltage, that will tell us what the equivalent resistance is. In this particular case, it makes some sense to make this a current source and to make it a 1 amp current source. 1 amp current source means that Ix is equal to 1. Therefore, 2Ix is equal to 2 volts. And so we find that V is equal to 2 volts. I is equal to 1 amp. Therefore, R Thevenin equal to R Norton is equal to 2 volts divided by 1 amp, which is equal to 2 ohms, as before. And so this is really quite an elementary circuit. It's a little bit of a challenge to get your head around what to do, but as you can see, you follow all the same rules and you end up with an equivalent circuit, and that equivalent circuit is the same every time. If it's a Thevenin equivalent, it is a voltage source in series with a resistance. If it is a Norton, it is a current source in parallel with a resistance. That is what the Thevenin and Norton theorems suggest, and it works out for us every time. All right, thanks.